equals GQ over 2m times the thing times L. So the G is this gyromagnetic spin factor. It's G. And that's what this paper is about, all right? And what's cool about this is that this is, I think they say the word. Okay, I think they state somewhere it's the most precisely measured quantity ever. And it's given as 2.0023193043718.
To find that certainty is only a few parts per trillion.
Per trillion, okay?
Is it still though? That seems to go back and forth about what is between general relativity and quantum mechanics.
What goes back and forth?
What's most highly calculated? It seems
Yeah,
like,
I'm not an authority on the absolute answer. All right? And so what happens is, you know, in some early theories it comes out to be 2, all right? But to do the full calculation, you have to do relativistic quantum field theory.
So this is getting at the stuff that I was talking about, right? Getting
Yeah.
at this.
Yep. Yeah. And so to do that calculation, what you have to do for relativistic quantum field theory is you have to do the Feynman diagrams. And what happens is they include these Feynman diagrams, all right? And those Feynman diagrams represent the best calculation we can make. And I think they mentioned...
No, they go further than that.
Oh, they can go further, but this is the best we're at this point. And this isn't all of them.
No, I think he says that they did,
720, I believe, somewhere I remember.
gee, well, they had a 91.
Oh, so 95, there were 72 diagrams.
Yeah.
Okay, even so, precision. Of which, so you can go up to 4 loop diagrams, and that's 891.
Yeah.
Okay, but the thing that I like to point out is whenever you see a loop, right? Like you see a loop inside of the lines, that loop is when you make a particle and antiparticle and they annihilate. That's kind of the physical interpretation. It's called vacuum polarization. It really is telling us something philosophically right, I think, about the world, perhaps right. Because what it's saying is that the experiment, to get all the experimental wiggles right, which means get all the numbers right, then you have to include that in nature, that those particle-antiparticle pairs are vacuum polarizing to give you this effect and to get the numbers right. Do you see what I mean? So the theory in these pictures, you know, if the pictures and the interpretation of the Feynman diagrams are correct, is telling us that what nature is really doing down there, which is pretty wild. Right? And that's why I always say when people have new theories, right? New theories are great and you should have them. But in physics, new theories are tested down to the plus or minus a trillionth. Right? And so if there's new physics there, the new physics is going to be less than a trillionth, right, of a part. And, you know, it's got to get everything else right. So anyway.
I think these last 6 are interesting.
What's that, the last 6? Yeah.
The
I mean, that...
the photon.
People write, you know, computer programs to generate the Feynman diagrams. And so that's what Brandon Green and I were doing. And we got pretty far in doing it. And it's a project that we could certainly, if anybody's interested, we could certainly continue. But we had good success in getting up to a certain point, and we've got some Feynman diagrams generated. Well, what we try to do is not just calculate the diagrams, but to do a calculation out of it. And so what we were able to do is we were able to write a LabVIEW program that got Feynman diagrams and generate some Feynman diagrams. So the next step is to turn them into calculations. All right, so if anybody's ever interested, I'm more than happy to work with you. All right, so the next part, let's look at addition of angular momentum. Okay? And this is going to be Gordon coefficients. So addition of angular momentum. Okay, and here's how I like to start. I like to start with a picture. Let's take an atom, or, you know, I start with an atom, but here's, you know, a spin 1 electron, if you want, and then here's spin 2 of an electron. And then if you want, here's the proton. Say you have 2 electrons. But the proton, I'll just call it the nucleus. Let's assume that the nucleus has no spin, approximately no spin. All right. Now, here's what I'm going to do. I'm going to draw my little cloud around there, and I'm going to say the following. I'm going to use Newton's laws. The sum of the torques external equals I alpha. All right? And I alpha can also be expressed as dl total dt, right? I alpha equals the time rate of change of the total angular momentum, right? So let's look at the external torques. If I'm not touching this, it's not in a magnetic field, nothing's going on, right? If this is making a magnetic field, this spin, let's do this. Let's say this spin 1 equals a magnet, south-north number 1, and this equals a magnet, south-north number 2. And these are making magnetic fields. All right, so now think of spin particles. By the way, here's how I see an atom. A hydrogen atom is the mu of the proton with a mu of an electron, right? Magnet of a proton, magnet of the electron, and then the electron's in an orbit, so there's also mu of the orbit, all right? But don't write that down unless it makes sense to you. But the new way of thinking about an atom and all these charged particles that are spinning is little tiny magnets. Okay? So if I look at the external torques, I'm not doing anything external to this. So how much torque external to the system is there? External, 0. So 0 equals dL total dt, which means what? L total equals?
Constant.
Constant. All right? So the only thing I can say about this is that L total equals constant. So I have an atom with a whole bunch of, I have like a regular angular momentum R cross MV, and then I also have intrinsic spin angular momentum, which is just spin, that's an angular momentum. All right? So the question is okay, so this is all I know is that it's constant. The next question is, well, what could it be? All right, I don't have any more information than it's constant, so what could it be? So let's look at a special case. Let's look at the case that we have S1 equals a half, and we have S2 equals a half. All right? So remember, I would write this in the following way. I would write it as a half MS1. And this equals a half MS2. So these are the projections. So I know they both spin a half. This first number just has to do with the vector magnitude. All right? All right, so if I have 2 spin half particles, they have angular momentum of a half, spin intrinsic angular momentum in half. What are the possible values of L total that I can have? If I only have 2 things, and the spin is each a half, what are the possible values I could have?
-1, 0, or 1.
Well, how about this? If they add like this, S1 and S1, all right, that would be S total equals 1. All right, and then the spins only come on up and down, right? So if they
next to each other, it's 0.
So if they go like this, it's 0, so S total equals 0.
So you can't get like
And if they go S down,
What's that?
So you can either get like 2 ups, 1 up, 1 down.
1 down,
or
yeah.
2 downs.
Yeah, or in general, like in general, let's say I had, here's another way to look at it. Say I had L angular momentum, I had L1 equals 3, and I had L2 equals 1. Okay, what's the most angular momentum I can have? 4. What's the least angular momentum I can have?
2.
2, all right. So I'm talking about the magnitude of the angular momentum.
You couldn't have negative
Alright.
4?
So the most, well, I'm talking about the magnitude. So here's an important thing. This number does not come in minuses,
Yeah.
okay? That will screw you
Like,
up.
if they're both in the same direction, it's 1, if they're in opposite direction, it's 0.
Right, so this you could have 3 and a 1, so this L total equals 4. And then the other thing you can have is this, where L total equals 3. I mean, L equals 2. So the rule is, here's the rule. When you have angular momenta, you have, when you add angular momenta, you go from L1 plus L2 is greater than or equal to L total, which is greater than or equal to L1 minus L2. Right?
You have the signs backwards now. If L1 and L2 is less than L total.
Well, I said it right.
You said it right.
So this is 4, yeah, is greater than or equal to L total, is greater than or equal to, thank you, is greater than or equal to 2. Okay. Now, what chunks, angular momentum is quantized, right? Okay? And it's quantized in chunks of h bar. All right, so if these are all in terms of h bar, what are the possible values I could have here?
For any number between, you have 4, 3, 4, 3, and 2.
So I could have 4,
3,
3, and 2. So L total could equal 4, 3, or 2. How about over here? I hate to switch around, but now when we go, oh, well, let me stay over here. So this is kind of like L4, well, let me write it like this. 4 ml, this is 3 ml, and then this is 2 ml, where mLs represent the projection now.
Yeah.
Okay, so how many projections could you have if you had a total of 4 angular momentum? So now you've got that your total angular momentum is a 4.
Projections can vary from positive 4 to negative 4.
Right, so you'd have, here's how I sometimes write it, 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. You could have those. And then over here you'd have 3, and minus 3, minus 2, minus 1, 0, 1, 2, 3. And then here you could have 2, minus 2, minus 1, 0, 1.
You should have 9, 7, 4, 5.
Yeah.
Depending on.
Okay. So first of all, look, this argument over here that says L is constant for the atom, the first thing is when you have 2 angular momenta, right, the total angular momentum has to be constant. So what are the possible total angular momentas that this thing could have? They could be where they're aligned completely up, or they could be aligned where they're opposite, or someplace in between. So your atom could have a total angular momentum of 4, 3, and 2. But if it has a total angular momentum of 4, how many projections could you have? That many. And if it had, okay, everybody get how that works? Okay. So I don't think that came across that clearly in the book. All right, but let's now get back to our, can I erase this now? Yeah. Okay. Now let's get to our two-spin system. So if I have a spin up and a spin down of a half, let's do it. Let's do it again. So S1 plus S2 less than or equal to S2
Greater than or equal to.
less than or equal to S1 minus S2.
Your symbols are backwards.
Okay, sorry, greater than or equal to.
You said less than, you wrote less than or equal to, but you want to flip the.
No, this is the way I want it written. As I've written it is right. Okay?
Are you sure?
Yeah.
Because S1 plus S2, that implies S total is greater than the total angular momentum. Just write the left side by itself. Yeah.
Yeah.
There we go.
Yeah.
Gotcha. Okay? All right, so what could we have here? A total spin angular momentum of,
1 is between,
this would be 1, greater than or equal to S total, greater than or equal to 0, in steps of 1. No, not a half, because the only chunks, and so spin,
even though they're half chunk.
the spin orbit, spin intrinsic angular momentum has a magnitude of a half. All right? But its projections are 1 chunk away. So you could have any
3 halves.
you could have any absolute amount, I guess. But the way you go from one to another is in chunks of 1 unit. So it is kind of weird that the fundamental chunk of angular momentum is h bar, yet the fundamental spin of a fermion, spin half, is a half of one of those chunks. Or from then on it goes up. But don't forget also, like bosons, remember when you quantize a boson field, a harmonic oscillator, the fundamental energy is h bar over 2, right? And it's that h bar over 2 is kind of the same thing here, but then the photon has, or the chunk of a boson field, the chunk of energy is h bar omega. So you go up by an h bar omega for a harmonic oscillator, and here you go up by a chunk of h bar for spin and momentum. Anybody understand what I just said?
The H bars are not here on the plot.
Even though it comes in half, it still goes up by 1.
You're right. And it's kind of interesting to me that the fundamental thing that the electron has a half an h bar, and the fundamental ground state of a harmonic oscillator is h bar omega over 2. And this is h bar over 2. I never thought of that. Okay, so in any case, if you have 2 spin half particles, what are the possible total constant angular momentums that you can have? There's just 2. 1 or 0. So we have a 1 and a 0, so S total. So the system could have an S of 1 and then an MS, and then a 0 or an MS. So let's write this complete. Let's write S total, MS total equals this, or it could equal those with MS total. Now, if it is a spin 1, a total intrinsic angular momentum of 1, what are the possible values of MS?
-1, 0, or 1.
So this could be 1, -1, 0, or 1. So there are 3. And then what could this be?
0, 0.
0 and 0. Okay, so what we say is this, is that when we couple 2 spin halves, we get a triplet and we get a singlet. So in other words, I don't know which one I'm going to get, but I know when I put together 2 spin half fermions, that I have one system that's a triplet, that it has 3 different quantum states, and the other that's a singlet.
So this is group theory too, right?
Okay, so this is what Dale mentioned, this is group theory. So if you were doing group theory, I'm really not an expert on it at all, and I can't add too much to it. The way it's written, group theory, these are all group theory ideas. So in group theory, it would be written like this. It would be written as an SU2 cross an SU2, which is essentially, this is a special unitary group of dimensions 2. So this is a 2D special unitary group 2, cross a special unitary cross 2. So this is a spin half. A spin half. So what are the dimensions of a spin half space? What are the basis sets? Up or down. So what are the dimensions? 2. So it's like a 2 by 2. So it would be a 2 cross 2. And what you say is they equal a 3 plus a 1. Okay? Now, I completely understand how to get the 3 plus a 1 by doing this,
Not so clear with the group theory.
but I'm not clear on the group theory. I'm not good enough in the group theory to say anything that would help you guys. All right? So, for example, when you do particle physics, and you have quarks, right? The early models of the quarks had 3 flavors of quarks, up, down, and strange. All right? So guess what SU, what the dimensions of that space would be?
SU3.
SU3. So for 3 quarks, up, down, and strange, you'd be an SU3 cross what? If you couple 2 quarks together, SU3. All right? And this equals an 8 plus a 1. So a singlet and something that's an 8. All right? So if I have, so using group theory and I combine 2 quarks, up, down, and strange quarks, it means that I could come up with what's called an octet and a singlet. Now, if I put together 2 quarks, what is that coupling called? It's called a meson. A meson. Baryon is a 3.
It's 3, huh?
So these are the mesons. All right? And so the mesons predicted that they should have like a quartet, an octet, and a singlet of particles that were mesons. And lo and behold, when they went and they looked for them, what did they find?
More than that.
They found that, all right, with the up, down, and strange quarks.
Wasn't that though, there was one missing?
Yeah, so I don't know how that goes.
Because I remember Galman, he predicted one, and then it popped
Yeah,
up.
there's some reason that that's not there. It might be in the next one, but check this out. If you want to form a baryon, like Jeremy said, all right, how many quarks are in a baryon?
3.
Okay, 3. So you would go SU3 cross SU3 cross SU3. Oh, and by the way, I think you have to make this, you have to put a bar over it because you have to have the anti-color, because when you're adding color, the quarks have to be color anti-color, so they're neutral. But anyway, when you do this, and this is what I don't know, you come up with a 10 plus an 8 plus an 8 plus a 1, something like that. Don't quote me on that, I forget, so. All right, but anyway, it says that when you, so the group theory says that when you put together these 3 quarks, you should come up with a grouping of a 10, an 8, an 8, and a 1.
That's your right, that's 27.
Okay, that's 27. Yeah,
Mathematically, it
that's
comes
your
out right.
choice. What's that?
Mathematically, it comes out right.
Yeah.
8 times 3 times 3 is...
Yep, so those are the possibilities. All right, and this is what Murray Gell-Mann was doing and proved like or this is when the theory of quarks really took off. All right, that all of a sudden that the quarks and this symmetry and the group theory started predicting the properties of the quark combinations. All right, but can I finish for 3 minutes and I'll get done?
Yeah, that was the other class. What time's the other class?
Yeah, but thermophysics coming in here in a few minutes.
At what time?
Class starts at 2 o'clock.
At 2, so we have a couple minutes, all right?
Yeah.
Okay, so let me finish this up, all right? Okay, so that was just a big side note, and I would like to be able to say more about that. All right. Okay. Okay, so we have a spin 1, which equals an S1 MS1, and we have a spin 2 equals S2 MS2, and these both are equal to, this is a half MS1, and then what's this one going to be?
Half MS2.
It's always a half MS2, and it's these things that can be different, that can be
I'm just
numbers.
going to be
Okay,
whatever.
so let's do this. Let's build, for example, let's build the 1, 1. So let's build S total, MS total. Okay, so how could I build a 1, 1? It has to have a total of 1 and a projection of 1. So let's do this. How about if it equals this? Isn't that? What if this was S1 and this was MS1? Right? So that's only a half and a half. But then we multiplied it times this thing, S2, and this was an MS2. So this all together came out to be something like this. This is MS1 plus MS2. Okay, that kind of works. I don't know, not multiply it. But if you added, sorry, instead of, you can't really multiply them. If you add vectorially, okay, then it equals this. And this would come out to be MS, a half is going to be a half, and MS1 and MS2 are each your halves. So when you add those up, they come out to be MS equals 1. So this equals, this is how they write it. Okay? But I want to caution you, what that really equals is this is a half times a half. Right? Because this is a spin up of particle 1, which is a half, and it's an up, so it's plus a half. This is particle 2, which is a half, so that's also up, it's a half.
But they're added together,
They're not added together. This is a...
because you can't, can you do that with ket? I thought that was disallowed.
You can, because what you're doing is you're making a basis set. So what you're saying is this, is you're saying that these, here's the best way to do it. These are my uncoupled bases. All right, my uncoupled basis, like that's a good basis set and that's a good basis set. If I want to find a coupled basis set, right? So now I'm looking for, this is almost like separation of variables, right? And when you separated variables and then brought them back together, how did you bring them back together? Did you multiply them or add them?
Multiply.
You multiply them. So a coupled basis set would be like S1, MS1 times S2, MS2. And so here's what you're looking for. You're looking for S total, MS total. This is really what we're getting at in Clebsch-Gordan coefficients. Equals, you want, so this is coupled. They're coupled together, and you want it to be in terms of this new, bigger, uncoupled, a new coupled basis set. So you would write it as the summation over C, S1, MS1, S2, MS2, of C, S1, MS1, S2, MS2, of S1, MS1, S2, MS2. So you're building that total thing as a linear combination of my new coupled basis set. And my new coupled basis set I just got from my two uncoupled basis set, like it was separation of variables. So for this one, it's clear, you know, what is my coefficient? C for that one?
1.
It's just 1. It doesn't need anything else. All right, try this one. Try 1 minus 1. So that's going to equal, if I drew a picture, it would look like this, plus this one. This is S1, this is S2. But what is this? This is minus a half now, and this is minus a half. And so what is that going to equal over here?
1/2 minus a half, and 1/2 minus a half?
Yeah, so it equals this. It equals a down, down, in that very abbreviated notation, 2 down spin halves. But it also equals a half minus a half